4.6, Applications and Models of Exponential Growth and Decay. We've got a formula for exponential growth and decay that looks something like this. Y equals y0 times e to the k times t, where k is a constant, and y0 is how much you started with, and y is how much you end up with after a certain amount of time. The amount of time it takes for a quantity that grows exponentially to become twice its initial amount is its doubling time. Example 1, the table shows the growth of atmospheric carbon dioxide over time. A, find a different exponential model using the data for 2000 and 2175. I don't really know why it says different. We're just going to find an exponential model here. Let the year 2000 correspond to time equals 0. We're going to start with our formula that we learned on the last slide, y equals y0 times e to the k times t. And we look at the chart to see a couple of things. We're looking at the years 2000 to 2175, so we would notice that the time span there is 175 years. But we're concerned with these y values. These are our y values. Looks like y0 is where we started at 375, and the final amount would be 1090. So plug in the values into the equation that we can. We've got 1090 equals 375 times e to the k times 175. Basically, we're just solving this problem. We're trying to find k. So we would need to divide both sides by 375. And that looks like it is about 2.906 repeating. So that equals e to the 175k. If I'm continuing to solve this equation, then I would need to get rid of the e. I'm going to take a natural log on both sides. So natural log of that answer. If I use the answer button on my calculator, I don't have to worry about rounding off. So if I take the natural log of both sides to get rid of that e, I would have 1.067 approximately equal to 175k. Divide by 175. And k is about 0.006097. Let's plug that back into our model. Y equals, and the starting amount for us was 375, so we're going to use that. And e to the k was 0.006097t. That would be our new exponential model. Part B, use the model to estimate when future levels of carbon dioxide will triple from the 1951 level of 280 parts per million. So that's going to triple. 280 is going to triple, and 280 times 3 is 840. So 280 is turning into 840, or tripling that. So let's just put that 840 in place of y in our model. 840 equals 375. E to the 0.006097t. That's going to allow us to find when that will happen, what year that will happen. So again, we're going to divide by 375. .24 equals e to the 0.006097t. To get rid of that e, we're going to need to take up natural logs. So we will do a natural log of both sides. Natural log of 2.24 gives me 0.80648 approximately equals 0.006097t. And lastly, of course, we're going to divide by that number to isolate the t variable. I get approximately 132. T is about 132.3 years. So we want to know when that happens. It's going to happen 132 years after we started, but remember we started in the year 2000. So if we started in the year 2000, or this formula, this model starts in the year 2000, let's add on that 132. We're talking about the year 2032. The carbon dioxide level triples in the year 2132.